Hey guys, these are your guided notes for lesson 6.3. We're going to make confidence intervals for population proportions. This is very, very related to the confidence intervals that we're making for the mean. The only difference now between your two numbers, we're not going to say that's where the population mean could be. We're saying between these two numbers is a population proportion. So we'll talk about a proportion in a second, but it's related to the point estimates we've already done. We're still going to do the confidence interval, and we're still going to find minimal sample sizes to get a certain error. Like I said, it's all very related to what we did last sections. So for this example, in a survey of 1,006 adults in the U.S., 181 said that Abraham Lincoln was the greatest president. If I want to know the proportion of people in this sample who think Abraham Lincoln was the greatest, basically what I'm asking when I say proportion, I just mean what percentage. So you would just, that's the reciprocal of what I should have. It should be 181 over 1,006, the total that said yes to whatever the question was out of your total sample size, which when I put it in my calculator is approximately 0.18. So around 18% think Lincoln is. So your point estimate for the population proportion of successes is denoted by that letter P, is given by the proportion of successes in a sample. So just like before, the point estimate for a population mean is the sample mean. The point estimate now for a population proportion is your sample proportion. Now the notation for a sample is P with a little hat. We literally call it P hat. So P hat is going to be equal to the number of x's over your sample size n, which is why I had the reciprocal of the right answer in the first part of this. So x is your number of successes, n is the sample size. The point estimate for the proportion of failures would be Q hat, 1 minus P hat. So example 1, find a point estimate for the population proportion of adults who say Lincoln is the greatest. That would be the 0.18 we already found. But a confidence interval for your population proportion is where you take that point estimate, our P hat, and you're going to add an error onto it and subtract an error onto it so that you could say that your population proportion is somewhere between here. In this case, your error formula is your z sub c, a critical value that we found before, times the square root of P hat Q hat over your sample size, over n. The probability still is going to be the c. That confidence level is still the same as what it was before. We talked at the end of second semester about how you can only use the normal distribution for things if NP is greater than or equal to 5 and NQ. This same thing holds true. We technically should test this every time, but we're not going to go through the effort every time. But really you should. In order for this to be true, N times P hat from your sample has to be more than 5, so does NQ hat. That one too. Okay, here we go. So when we do this, you're going to find your sample statistics. You're going to make sure that you identify N and X. You're going to find your point estimate P hat just being x divided by n. You're going to make sure that you are able to use the normal distribution in P hat and NQ hat, which again I tend to skip, but you really should make sure. Find your critical value the same way we've always been finding it. You guys will use inverse norm because none of you have to use the table since you all have the appropriate calculators. We're going to find our margin of error like we always have been. This is a different formula for it now though, so you're probably going to want that on a note card eventually. And then you just find your endpoints. Take your error and add it and subtract it from your point estimate, from P hat in this case. So what that looks like. For example 2, a sample of 500 nursing applications included 60 from men. I want the 90% confidence interval for that true proportion, the population proportion who apply for a nursing program. So we're given sample size is 500, number of men who applied were 60, and the confidence level is 90%. So we can find our critical value. If you've got it memorized, great, but we can still find it. I will want the positive answer from inverse norm. Remember, we always take 1 minus your confidence level. That gives you the two tails combined. Cut that in half to find one of the tails. Using inverse norm on the standard normal curve gets you this value. We can also find P hat pretty easily because if we take our x divided by n, 60 divided by 500, you can find that 3/25 is our proportion, or just 12/100. Once we have those, we can plug everything into our error formula. So 1.64, the square root of 0.12 times 0.88 divided by 500. You should get approximately 2/100 out of this. So if you put that and add it and subtract it from your point estimate, you're going to find that the population proportion is between 10/100 and 14/100. So we could say that if you kept doing intervals over and over and over and over again, intervals just like this from samples, 90% of your intervals will have the population proportions between them. 10% of them would be wrong. So like I said, very related to what we were doing. So example 3, very similar. 100 people, 27 were obese. I want the 90% confidence interval. So give you N, X, and C for this one. So you can find your critical value. You can find p hat. This kind of is an unnecessary example because it's so similar to what we just did. But you can find your error by N sub C times the square root of p hat q hat N over N. So you find your error is 7/100. Adding it and subtracting it from 0.27 gets me 0.2 to 0.34. One way to increase the precision of a confidence interval without decreasing the level of confidence, meaning I want to be more precise, but I don't want to change my level of confidence. I don't want to go down to 90% instead of 95%. One way to fix that is just sample more people. So if you want to find your minimal sample size, if you're given a confidence level that you have to keep and you're given a margin of error that you have to keep, this is your formula for it. This is just the formula we had that solved for N. So p hat q hat times the quantity of your critical value over your error squared. Definitely going to want to have that down on a note card. This formula assumes that you have preliminary estimates for p hat and q hat, meaning from some previous sample, the sample turned out to be 30% said yes. If they don't give you preliminary estimates, you have to use 50% for p hat and q hat. So if they give it to you, use what they give to you. If they don't give something to you, you have to use 50%. So for this one, a researcher wishes to estimate with 95% confidence the proportion of people who own a home computer. A previous study showed that 40% have a computer at home. I want to be accurate to within 2% of the true proportion, and so I need my sample size necessary. So I'm using my formula for finding the sample size. I'm told p hat is 40%, so that means q hat must be 60%. You can find your critical value if you don't have it memorized for a 95% confidence level, and it's divided by my error, which is 2/100 in this case, because I have to be accurate within 2% of my actual proportion. So I'm going to square that. This rounds to about 2,305 people. Example 5 does not give me a preliminary estimate. All I know is I want to be 90% confident, and I want to be within 5% of my true proportion. So when that happens, you're still going to use the same formula, but you're just going to plug in 0.5 for p hat and q hat. Everything else turns out the same. You're still going to know your critical value, you put in your error. This rounds to about 269 people. And that's all we're doing. So make sure that you are getting these formulas down. Go back and rewatch and pause things if you had issues with it, if I moved too fast, whatever. But I'm hoping this is close enough to the interval for the mean that it hopefully isn't too confusing. So good luck.